Hello, everyone, and thank you for joining today's EthicalChem webinar, where we'll cover surfactant oxidant technologies for subsurface contaminant remediation. I'm Dan Socci, CEO of EthicalChem, and with me here is Samantha Higley. Sam is an environmental scientist with EthicalChem, and we'll be hearing from Sam shortly. And also with us is Geeta Dahal. Geeta is an environmental engineer with EthicalChem, and she'll be available as we get into fielding any questions that come up. You're probably familiar with webinar format in terms of the tools available, but you do see in the upper right the ability to submit questions. So you can just type them out and click the send button on the right, and we'll plan to field them at the end, but we'll try to keep an eye on them. If any are timely, we may cover them as we go along. Our format today is I'll make a few comments about the company, get you grounded on EthicalChem, who we are, what we do, and then I'll turn it over to Samantha, and she'll take you through our technologies, and then we'll wrap up with cases. So with that, I'm going to take you through a few comments on the company. EthicalChem develops and manufactures chemicals for multiple applications in two industries, environmental and oil and gas. Most of our technologies use specialized plant-based, readily biodegradable surfactant blends. Typically, our surfactants are used in conjunction with industry-standard oxidants such as persulfate, hydrogen peroxide, or permanganate. And we've also developed several proprietary processes for use in environmental and oil and gas applications. EthicalChem operates with a flexible business model. We have customers who are familiar with our technologies and purchase our surfactants alone. And with the surfactant purchase comes a license, a one-time project-specific license to use our technologies. Often clients would like us to design a treatment solution, provide all the chemicals, and be on site to oversee the treatment startup. And some clients prefer that we are the prime contractor for a treatment, in which case we bring all the necessary resources to a site and are responsible for all aspects of an implementation. We also offer services, and we'll cover surfactant screening as we go through the presentation. Sam will cover that. And also in the case studies, I'll make some comments on a treatability study example that we've done. EthicalChem holds 14 patents with another 6 pending, and we continue to undertake R&D. And I'll preview right now that we have a new peroxide activator that's due for launch soon, so keep an eye out for a webinar invite introducing that new product. Our technologies are field proven and have been implemented internationally in 14 countries with over 100 implementations. So our presentation today will focus on 2 technologies for environmental applications: Surfactant Enhanced Product Recovery, known as SEPR, S-E-P-R, and Surfactant Enhanced In Situ Chemical Oxidation, S-ISCO, S-I-S-C-O. SEPR is an extraction technology which uses an EthicalChem surfactant and low dose of hydrogen peroxide for removal of bulk free phase from the subsurface. The free phase contamination can be L-NAPL or D-NAPL, including coal tar and creosote. And on the lab study, we'll take you through a 6-oil example as well. S-ISCO, again, Surfactant Enhanced In Situ Chemical Oxidation, also uses an EthicalChem surfactant and any one of several industry standard oxidants, which, as I mentioned before, are typically persulfate, peroxide, or permanganate. This technology provides in situ contamination desorption, emulsification, and destruction. Sam will cover in greater detail the combined use of an optimized surfactant with an oxidant makes S-ISCO a very different remedy than either use of an oxidant alone or surfactant alone. Both SEPR and S-ISCO have been awarded multiple patents. Now, I mentioned just now on that slide we just covered that S-ISCO, by use of a simultaneously injected surfactant and oxidant, is highly differentiated from activated oxidant alone. Conventional in situ chemical oxidation, ISCO, is very effective at destroying contaminants which are in the aqueous phase. ISCO has some but limited impact on non-aqueous phase liquids, as it can only address the point of interface between NAPL and the aqueous phase. Sam will take us through in greater detail the differentiation of an ISCO aqueous phase treatment and a SISCO treatment, which delivers NAPL to the aqueous phase. From a treatment results standpoint, the difference is that SISCO will have much greater impact on the source of contamination in the soil. By desorbing the contamination and bringing it into the aqueous phase, SISCO will provide greater contaminant degradation and avoid or minimize contaminant rebound. So with that, my thanks again for joining today. And now I'll turn it over to Samantha Higley. Sam, as I mentioned, is an environmental scientist with EthicalChem.
Thank you, Dan. Hello, everybody. As Dan just mentioned, surfactants can provide a significant advantage to Chemox technologies. With that said, there are considerations when selecting and applying them to optimally treat your site. We will start by looking at a quick background of surfactants, then when to apply surfactants. Not all sites may need them, and some may require different technical applications, such as desorb and remove versus desorb, emulsify, and destroy. Then we will discuss how to effectively apply surfactants at those sites where they could be effective. A surfactant is a compound that lowers the surface tension between two liquids or a liquid and a solid. For remediation, surfactant use is aimed at lowering the interfacial tension between the groundwater phase and the hydrophobic organic contamination. The effectiveness of surfactants lies within their structure. They are long molecules which contain one end that is attracted to water, hydrophilic, and one end that is not attracted to water, hydrophobic. When surfactants are mixed with water, they form what is called a micelle. A cross-section is shown over here on the right, where the hydrophobic ends orient themselves to the inside of the micelle away from the water, while the hydrophilic ends orient themselves on the outside micelle toward the water. When other hydrophobic molecules are present, such as organic contaminants or NAPL, they end with the hydrophobic end of the surfactant and are encapsulated in the center of the micelle. So how can this be used to our advantage in remediation? The formation of these micelles lowers the interfacial tension between organic contamination and the groundwater phase, desorbing and releasing contaminants bound to soil and bringing the contaminants into the aqueous phase. What does this accomplish? Since oxidants are in the aqueous phase, solubilizing and emulsifying these otherwise insoluble contaminants significantly increases their exposure to the oxidants, allowing them to be readily treated. This not only treats contaminants more efficiently, but also extends the capabilities of Chemox technologies to more heavily contaminated sites. Here is an illustration shows how contact is significantly enhanced through use of surfactants. On the left here, we see how a non-aqueous phase liquid has very limited contact with the groundwater where the oxidant is present. There will be some dissolved phase, but the natural solubility level of these organic contaminants is very low, so substantial free phase remains. When surfactant is added, the contaminant becomes emulsified and the NAPL is brought into the aqueous phase via micelles, which greatly increases the surface area exposed to the aqueous phase oxidants. For example, EMOS-3 surfactant typically exhibits a pH solubilization rate greater than 10 times than groundwater alone. It can be oxidized much more efficiently, and sites which would have been impractical to treat using Chemox technologies are now feasible to treat with Surfactant Enhanced In Situ Chemical Oxidation, SISCO. We will now take a look at a third-party study completed by the University of Madrid, which compared traditional ISCO versus SISCO technology for treatment of PAH contamination in soil.
Sam, before we get to the test results, I'd just like to get everybody grounded in how this particular test came about. University of Madrid representatives saw a presentation that we were doing at a conference in Europe some years ago, and they followed up with us indicating that they were considering funding a test at the university to compare ISCO and SISCO, and we were delighted that they followed through and we sent samples out. So the testing was completely unsolicited and independent. Our role was just to indicate that we would provide a surfactant sample, provide some advice on dosing, and they undertook it. Both the decision to do it and the approach was entirely theirs. And we think the results are pretty interesting. So, Sam, I'll turn it back to you.
Great, thank you. This research evaluated 4 contaminated soil columns, where one was a control pumped with water only, one was a surfactant flush using EthicalChem emul surfactant, one was a SISCO treatment with emul surfactant and alkaline activated sodium persulfate, and the 4th was ISCO treatment with alkaline activated sodium sulfate. Each column was pumped with influent for 25 days. At the end of the test, both the soils and effluents were evaluated for each column, and a mass balance was completed. Following the 25 days of treatment, you can see the control column here, labeled CB, still contained about 95% of the original TPH in the soil, as demonstrated by this blue column here. The surfactant flush column, labeled CF, shows close to 100% of the TPH eluting in the effluent with very little remaining in the soil, as demonstrated with this red bar here. The SISCO column, labeled C-SISCO, reveals trace amounts of TPH remaining in the soil and no TPH in the aqueous phase. The last column, treated with ISCO, labeled as C-ISCO, showed the effluent was oxidized as it was in the SISCO column. However, over 30% of the contaminant remained untreated on the soil. This would be the source of the rebound in groundwater, typically associated with traditional ISCO treatments. Summarizing the University of Madrid tests, results supported the advantage of using surfactants for complete or near complete removal of contaminants from soil, as shown in the surfactant flushing column as well as the SISCO column. For removal as well as destruction in the aqueous phase, SISCO treatment showed a clear advantage over traditional ISCO treatment, which was unable to desorb and destroy over 30% of the soil contamination. As we have seen, surfactants can provide a significant advantage for chemical oxidation technologies. However, not all sites may benefit or need surfactants. Consideration needs to be given to the characteristics of the contaminant or contaminants present, such as hydrophobicity. Is the contaminant naturally very soluble or insoluble in groundwater? And how much or what phase of the contaminant is present? Is it very little and only exists as a dissolved groundwater plume? Is it sorbed to soil? Or is there enough that a measurable free phase are seen present? Sites which are lightly contaminated and or contain contaminants that have higher solubility in groundwater may not require surfactants because their contamination is already primarily present in the groundwater phase with the oxidant. On the other hand, sites that are heavily contaminated with high soil concentrations and or free phase present and sites with more hydrophobic contaminants will benefit from addition of surfactants during chemox treatments. If you have a site which could benefit from surfactant enhanced technologies, it is important to apply a surfactant best suited for a particular site. Surfactants are not a one-size-fits-all solution for remediation. In the same way you wouldn't use the same soap for dishes, clothes, your hands, cleaning services in your house, and so on, surfactants perform better with different contaminants and different oxidants. Most importantly, not all surfactants work well or are compatible with oxidants. Using a non-compatible surfactant with an oxidant could greatly impact your experience and success with surfactant use in remediation. Before recommending a surfactant for a site, EthicalChem can perform a surfactant screening test. This test is generally done at minimal or no charge, or as part of a larger treatability test, depending on client requirements. When screening surfactants for performance with NAPLs, the NAPL is measured into vials followed by various surfactant solutions. Vials are gently shaken and evaluated against a control which contains only NAPL and water. As you can see in the first vial here, NAPL and water alone is stuck to glass and does not mix with the water phase. Even after shaking, as seen over here, the NAPL remains smeared on the glass and did not mix with the water as we would expect. 5 different surfactants were evaluated in this test. As you can see, they had various effects on this same site NAPL. The surfactants in vials 2 and 3, here and here, did not perform well for this NAPL, and it remained stuck on the glass. The surfactants in vials 4 and 6, here and here, successfully removed the NAPL from the glass but did not emulsify in the aqueous phase. Instead, they desorbed and created an extractable layer of NAPL, which make them good options for the SEPR process. The surfactant in vial 5, as seen here, is the best choice for our S-ISCO process because you can see it removed the NAPL from the glass and also created an emulsion, where the NAPL is now in the aqueous phase and readily accessible to the oxidant. In the same University of Madrid study we discussed earlier, the research group evaluated 2 different surfactants for compatibility with sodium persulfate prior to deciding which surfactant to use in their ISCO versus SISCO column study. They compared a commodity surfactant with the EMULS-3 surfactant. These results showed that persulfate decomposition was much greater in the commodity surfactant, as shown by the small amount of persulfate remaining after the first pour, as you can see right here. This compared to the EMULS-3 surfactant, as you can see up here. This demonstrates how not all surfactants are equally compatible with oxidants. From these tests, they decided to proceed with EthicalChem EMULS-3.
Sam, before we leave this slide, I'd just like to clarify that when we use the term commodity surfactant, we are referring to a surfactant that's widely used in remediation as a flushing surfactant. So it's not that when we say commodity surfactant, we're reaching for or the University of Madrid, I should say, was using a surfactant that, as you pointed out, might be for an entirely different purpose. So it is a popular remediation surfactant, but I think the point that came out here is that it's not designed, as you were saying, to be compatible with an oxidant, and that came out in the test. Yeah, thank you.
So here we have photos from the tests which also visually show the incompatibility of the commodity surfactant with the alkaline activated persulfate, as you can see here. Unlike the EMULS-3 solution over here, which stayed as a flowable solution with alkaline persulfate, the commodity surfactant solution here gelled, creating an unusable mixture that could not be distributed into the subsurface. Here is another performance comparison done on the same site NAPL with 2 different EthicalChem surfactants, both of which have performed well on various different applications. Seen here in the top left photos, the MSX7 surfactant, as seen here, removed the NAPL from the vial walls and created an emulsion. On the right, the AFX9 surfactant did not affect the NAPL, leaving it stuck to the vial walls, and also you can see nothing has been emulsified in the solution here. These next photos are after letting the vial settle. The MSX7 has some settled NAPL phase on the bottom, but some remains emulsified. Again, nothing is on the glass. The AFX9 has streaks of NAPL on the vial walls and nothing emulsified. These bottom photos show the vials immediately after the air turned upside down. You can see the MSX7 vials have created an easily extractable mobile NAPL phase where the NAPL readily fell off the bottom of the vial. The AFX9 vials still not affected this particular NAPL, and it remains thick and stuck to the glass. To appropriately apply a surfactant at any particular site, the most effective surfactant must be selected, as we have seen in previous slides. Proper dosing of the surfactant and oxidant must be used. The surfactant and oxidant must be implemented simultaneously to ensure oxidation is taking place at the same time the contaminant is being desorbed and emulsified. This is where it is also very important to make sure the surfactant is oxidant compatible. Strategic monitoring around the site ensures the oxidant and surfactant are dosed appropriate and are traveling to intended areas. We typically have contingency plans in place, such as reducing flow rates, injecting oxidant alone or oxidant fronts, changing injection locations or extractions, etc., especially at sites in close proximity to sensitive receptors. Now we will take a closer look at our patented technologies, S-ISCO and SEPR. Our Surfactant Enhanced In Situ chemical oxidation technology uses proprietary surfactants simultaneously injected with oxidants best suited for site conditions. This extends the applicability of traditional chemox technologies to sites which are much more heavily contaminated than typically addressed with chemical oxidation. S-ISCO addresses the sources of contamination, providing clean groundwater as well as soil, and therefore eliminates or minimizes rebound associated with traditional ISCO implementations. Here is a visual showing how S-ISCO works in the subsurface. Both the surfactant and oxidant are injected into the subsurface. Sorbed contaminants are emulsified by the surfactant and brought into the aqueous phase. Here they are readily oxidized by aqueous phase oxidants, providing thorough removal of contamination and avoiding rebound. Although S-ISCO can address more heavily contaminated sites than traditional chemox technologies, there can be cost and time limitations when treating bulk phases of NAPL. SEPR technology can be implemented at those sites where bulk NAPL is present to more cost-effectively treat the contamination. SEPR uses proprietary surfactant blends simultaneously injected with low doses of hydrogen peroxide to efficiently remove free-phase contamination. The peroxide is added as a physical advantage, where the hydrogen peroxide decomposition provides physical agitation to loosen the NAPL, making it easier for extraction. SEPR can be implemented as a single technology or prior to S-ISCO. Here's another visual which shows the SEPR process. SEPR fluid is injected consisting of surfactant and hydrogen peroxide. The surfactant desorbs and emulsifies the NAPL, while the physical agitation from peroxide decomposition loosens the thick, bound NAPL. This helps loosen and facilitate movement toward recovery wells. Residual contamination may remain, which, depending on site cleanup requirements, may be acceptable to meet site objectives or may require follow-up S-ISCO treatment. If a site has bulk NAPL but requires achieving low criteria levels, we can combine the two technologies. Here is a site with bulk NAPL phase in the subsurface. SEPR chemicals are injected. The physical agitation from peroxide decomposition loosens the NAPL, and the surfactant emulsifies it. The bulk NAPL phase and emulsified plume is extracted from recovery wells. Residual NAPL may remain, which could recontaminate the groundwater phase. Treatment chemicals are then changed from SEPR to S-ISCO. Extractions are ceased, and extraction wells can be used as injection wells. And S-ISCO surfactant and activated oxidant are simultaneously injected. Residual contaminants are desorbed, emulsified, and oxidized in place, resulting in clean soil.
Great, thanks, Sam. I'd like to take everybody through a few case studies now. And let's see, we'll make the switch here momentarily. There we go. So our first one is actually a treatability study. I mentioned earlier in terms of our business model, we do lab work. Sam covers surfactant screening, and we do full treatabilities. And this one is 6-oil, where we'll walk you through use of soil columns. Here, as I said, it's 6-oil, and in this particular treatability, we were demonstrating the effectiveness of both SEPR and SISCO. So what we did there first was surfactant screening, and as you saw before, we take a look at how the surfactants, again, these are all EthicalChem surfactants. They've all performed well in the field, but we find out which one is the best suited to a particular contaminant and site environment. So here what we saw is that the far right vial produced results for SEPR. So we've got a lot of the contaminant, virtually all, has come off the glass, and we've got a layer that can flow to an extraction well. As we mentioned, we use hydrogen peroxide to introduce buoyancy, some lift, and that will enable that layer to be extracted. To the left of that vial, the highlighted vial, that would be what we would be looking for SISCO. So that is emulsified contaminant in solution, and that would lend itself to in situ destruction, a lot of surface area readily available for oxidation in the aqueous phase. And as part of this study, we also did a surfactant screening on site soil. This is not a visual exam, so I can tell you that that was the selected outcome, but it was measured based on the TPH reading. So the surfactant that delivered the highest desorption of TPH into the effluent was the best surfactant for this particular site. So with our selected surfactants, we then proceed to our columns. We had a control for 28 days with DI water flush. In the SEPR column, we used Emulse 10, so that would have been that most right vial we just showed you on the left side. And that was for 14 days of SEPR. And then we had a soil column where we were doing SEPR, Emulse 10 for 14 days, and then we used Emulse 3 with SISCO chemistry for the remaining 14 days. So that's combined SEPR SISCO. So here's a look at the SEPR treatment underway. First, a visual on columns. You can start to see that the two SEPR treated columns are showing more degradation of the contaminant than you're seeing with the control on the left. And also, when you take a look at the effluent now, you can see that the control column is delivering a almost fully clear F, whereas the contaminant emulsified and coming out of the soil column is obvious in the two jars in the middle and the right. So in terms of how we did ultimately in this test, we got substantial reduction from the SEPR column treatment, but adding the SISCO step got us further along. So we're seeing reductions here from the initial soil of about 15,000 milligrams per kilogram TPH. Is a reduction of a little over 95%. Okay, we're on to a field case study now. This is a coal tar site in Queens, New York, and our location here in a densely populated area, mostly surrounded by high-rise residences. We were located very close to the East River, so we had an injection well less than 150 feet from the river. So ensuring that no contamination or any chemicals at all reached the river or got close to the river was very much of interest to all the stakeholders, including New York DEC. So what we were treating here, 41,000 pounds of contamination. As I said, coal tar, mainly BTEX, PAH, and naphthalene would be the constituents of concern. Quite a bit of NAPL at the site. Weather was a factor here. The treatment happened to be done not only throughout the winter, several months in the dead of winter, but in a very difficult winter, 2 blizzards and a lot of very cold temperatures, but everything proceeded to go very well. So our treatment approach was the Emulse 3 surfactant with persulfate, sodium hydroxide. quite a bit of fluid injected, just a bit over 1.2 million gallons, and it was 100 days exactly that we were doing injections at the site. So the results, we met the cleanup criteria, over 90% contaminant mass destruction, ground and in soil, groundwater, over 90% as well, soil gas, 100% reduction of benzene, ethylbenzene, naphthalene. As I mentioned, keeping track of the chemicals, where they were going, was very much of it. No NAPL mobilization, no vapor pressure increases. And the surrounding residents, when asked after the treatment, generally said they weren't aware anything at all was going on. And that was an objective here, was to avoid a dig and haul. There was the urban location disruption, as well as the dewatering costs being that close to the river, that made us a much better solution, a much more cost-effective solution than excavation. And we're pleased to say that we were down in the neighborhood, a few blocks away at another site in Queens last year, and we went down to see how the old site was doing. And as we had hoped, the library construction that was planned for the site is well underway. It's just about completed now, and it's due to be open summer of 2019. So the certificate of completion was issued of just a little over a year after we were done at the site. So on our case study, I have just noticed, I think that's dated on the bottom of that slide. So if anybody caught that must be a replacement date. So yeah, those photos are from last year, and I think we just happen to have a full photo of in construction with an older date at the bottom. I just noticed that for the first time. But anyway, so our second case study is from Texas, and this was a pipeline that had a persistent leak over the course of several decades, impacting the soil. So the consultant we work with there did a nice job of documenting the results. First of all, with our vials on the upper left, pre-treatment, we have a thin layer of NAPL visible from groundwater. Once the surfactant oxidant, the S-ISCO chemicals are added, you see a nice suspension of everything, including the contaminant in the vial. And then as we progress through the days of treatment, we get clearer, ultimately clearer groundwater. And we have some of the numbers here for you, pre-treatment, and then showing post-treatment the substantial reductions. Also a visual on soil. So moving from clearly impacted soil on the left to much cleaner soil on the right. And the numbers here came very well. So it's over 99% reduction of TPH in soil and groundwater, and over 99% reduction as well of BTEX. The next case study is creosote site, Bridgeville, Delaware, former wood treating facility. And here what we've got is a treatment of using SEPR and SISCO to address the creosote. Starting out with SEPR, the initial fluid recovery comes back clear. And then as we get to day one, we start to see some emulsified contaminant. Day two, quite a bit more. And by day three, we have extractions that are yielding quite a bit of emulsified creosote contamination. As we wrap up the SEPR extractions and we decide we're ready to go to SISCO, what we're seeing is most of the wells are generating clear or almost clear fluid. We have a couple with a amount of emulsified contaminant. But at this point, we felt that the subsurface is ready for SISCO. The treatment becomes more cost effective when you get out a lot of that heavy NAPL. And at the end of the SISCO treatment, we were seeing clear vials from all the extraction locations, all the monitoring locations. So ultimately, the treatment was sufficient to meet the client objectives. Next one is, this is a SEPR alone, so with extractions alone, addressing PCE, again, back in the New York City area. Occasionally, we have clients who prefer extraction only, or sometimes they're planning to do SEPR and SISCO, but they find that the SEPR extractions are sufficient. And in this case, extractions alone were used. This was a pilot test. I think the numbers are a little too small to remove, but to cover rather. But what you can see is as you desorb the contaminant, we get a spike up in PCE, but then it comes down. We've got it out of the soil, so the idea here was to treat the source, to desorb and emulsify the PCE, and then through the extractions we got reductions that were 25 times the baseline PCE concentrations, and ultimately we saw declines up to 83% in a relatively short pilot treatment. So this client is looking forward to doing a full-scale SEPR later this year. So that's everything we had, and we can take a look now and see what questions have come through, and we'll be happy to answer those. Okay, so the group so far has not submitted a question, so if anybody was attempting, it didn't come through. I do have one that if as you're giving that some more thought or trying to use the tool, I will comment on a question that does come up. We do have a question now on typical costs, and you know, we'd be happy to answer that any way that you'd like. I think our first reference point is compared to traditional ISCO. Usually the costs are quite similar actually for what would be a first treatment in ISCO. So usually we are able to offset the cost of the surfactant. We tend to use less oxidant because we are delivering the contaminant to the aqueous phase as well as emulsified particles with a lot of surface area. We also typically avoid the repeat treatments, so we tend to be quite a bit less than ISCO throughout the life of a site treatment with ISCO. So that's an answer framed relative to ISCO. People often ask that. I'd be happy to, if you'd like to post a different type of answer around costs, we'd be glad to address that. Another question came in about injection permits in California. Yes, we have had regional water board approval for our surfactants for several years now, and we have done work in California. The technologies have been used in California, yes. Now, percent peroxide, first we clarify that for the SEPR, so Surfactant Enhanced Product Recovery, the question is if we're using the same percent peroxide for each project, or do we vary from site to site? For Surfactant Enhanced Product Recovery, the answer is yes. It's typically 1% hydrogen peroxide. But for SISCO, Surfactant Enhanced in Situ Chemox, I'd say it does vary. Gita, do you want to add anything there?
Yeah, we have our experience at different sites that we have injected peroxide has been, anywhere between 4% to 8% peroxide for SISCO. However, as Dan said, we typically stick to 1%.
Right. While we're answering that question, I'll just piggyback and say I made a quick reference earlier to a new peroxide activator that we're working on, so we're just wrapping up the tests on that. One of the things we look forward to with that activator would be to be able to decline or decrease the dose of peroxide by having an activator that allows it to last longer. So we look forward to getting that out there, and we're just wrapping up the characterization on that product, but it looks promising. And again, would allow a longer lasting peroxide and give us a lower dose. Okay, I think we're clear on questions, and I think we are relative to the time allowed. We do have a few minutes, and we'll just offer a response to one question that does come up a lot, and then we'll see if there are any more that came in. So The question has to do with mobilization, and once you desorb a contaminant, will you have a persistent increase in groundwater concentration? And so therefore, how do we manage it? So what's going on is we just like to cover again that SISCO is the combined use of surfactant and oxidant. So what's happening is when that chemistry is traveling together, you have the emulsification and oxidation taking place simultaneously and quite quickly. So in our experience, average groundwater speeds do not carry the emulsified contaminant very far from the injection well prior to destruction. So at any site, of course, we do have ongoing monitoring plans and contingency measures should we see the contaminant go farther than we were expecting, but so far that has not been the case. And to give you a little more context first on the monitoring plans, this would be the type, if we were responsible for the implementation, this would be on the top, the type of sampling that we would be doing. So we'll take samples multiple times per day, keep track of the different types of chemistry and where they're going, contaminant as well. And then an example from the site near the East River said that was very much of interest to make sure that the chemicals were not going anywhere near the East River. And what we saw with SISCO is that when we looked at the monitoring, we got what we expected in terms of the chemicals traveling together, and the destruction was quite fast relative to the placement of the injection wells. And I can take you through a chart we've got here that maybe explains it a little bit better. So our colors are first the oxidant. So at the monitoring point, the oxidant spikes up first, it arrives first. Next, we have the black line is the emulsified contaminant, and then the green line is the surfactant. So as the contaminant spikes up, as you can see, it is bracketed by oxidant. So that's what we're looking for: oxidant before, during, and after as the contaminant flows through. And then you can see that the contaminant drops off sharply. So the continued flow is now showing that the contaminant has been destroyed as it hits this monitoring point. And we think, of course, a fair question is, okay, this is good at this point, down gradient from an injection well, but what's going on further down gradient? And again, as we would expect, we're seeing the three chemicals travel together, but we're seeing less of each. And once again, the contaminant declines down to very low, almost non-detect in this case, and further down there was non-detect in any monitoring points. So we hope that gives you a little bit of information. We do say in our experience that we would expect all the chemicals, and particularly the contaminant, to travel less than 30 feet down gradient from an injection well, given typical groundwater speed. So usually it's quite a bit less than 30 feet. Okay, so summarizing everything we covered today, in our experience, SISCO and SEPR, Surfactant Enhanced Extraction and In Situ Chemical Oxidation, extend ChemOx to be able to treat heavily contaminated sites. The focus is on providing clean soil. Clean soil, of course, allows clean groundwater, and the oxidant does work as it would in ISCO, cleaning any contaminant that either was or we introduced to the aqueous phase. By getting clean soil, we avoid or minimize rebound, and this allows us to treat a broad range of organic contaminants. We treat chlorinated solvents, of course, but often we're called upon to treat the heavier hydrocarbons at, as we said, heavily contaminated sites. All right, so with that, we're going to do one more check, if we can, for questions and see if anything new has come in. All right, doesn't look like we have any new questions. We did the webinar this morning. Good question that came up was, is the University of Madrid information available? And also, are the slides available? And the slides I don't think are posted yet to our website. We will get them up soon. Or if you want to email us, you can see our emails are visible here. So either me or Samantha would be happy to send any information out to you. If you have a particular site, we'd be glad to discuss it. The University of Madrid paper is available on our website. I think the link right now is in the news section, and we are going to try to move that to be a little more visible in the next day or so. All right, so Sam, I don't think we have anything new that's come in, right? Is that a fair assumption here?
Yeah, no.
Okay, great. Great. All right, well, with that, again, we thank everybody for joining us today. We hope it was informative, and please feel free to contact us with any questions or if you'd like to discuss a site. With that, we'll sign off.